Have you ever stopped to wonder how we actually know what a molecule looks like? I mean, really looks like. We can't just stick it under a microscope, right? It's millions of times too small for that. So, how do chemists figure out the exact 3D structure of these totally invisible things? Well, it turns out they have to become molecular detectives.
And that's the big mystery we're diving into today. We're going to uncover how scientists can listen for these tiny, secret signals that come from deep inside a molecule. And by listening to those signals, they can piece together its structure, atom by atom. It's a fascinating story. So ready to see how they do it? Let's get into it.
All right, here's our game plan. First, we'll tackle the huge challenge of seeing the invisible. Then we'll meet our star informant, the proton, and find out how it sends us a secret signal. After that, we'll see how the proton's electron bodyguards change that signal, how we crack that chemical code, and finally, how all of this lets us build a complete picture of the molecule.
Okay, first things first. The scale of this problem is it's mind-boggling. We are talking about mapping out things that are way, way smaller than a wavelength of light. So literally looking at them it's not an option. It's physically impossible. Chemists needed a totally different and way more clever approach.
The strategy they came up with is brilliant. If you can't see a whole building from the outside, maybe you can get someone inside to call you and describe the room they're in. And that's exactly the idea here. We need to find some reliable informants inside the molecule that can send out clues about where they are and what their surroundings look like.
So who is our number one informant? Who's our person on the inside? Well, it's the proton. You find one in the nucleus of every single hydrogen atom, and it just so happens to have a very special property that we can use to our advantage.
Get this, every single proton in the universe behaves like a tiny spinning magnet. You can picture it like a microscopic compass needle, always spinning and generating its own little magnetic field. This is the absolute key. This is what lets us get it to talk to us.
So here's how chemists put this to work. First, they take a sample of the molecule and stick it inside a ridiculously powerful magnet. And just like a bunch of compass needles, all our little proton magnets snap into alignment with that big field. Then we zap them with a very specific frequency of radio waves. And at just the right frequency, the magic frequency, the protons absorb that energy and literally flip over. When they do that flip, they release a tiny pulse of energy, a signal that our machine can detect. They're talking to us.
Now, you might be thinking, okay, but if every proton is the same, won't we just get one big, boring signal? And you'd be right. But here's the beautiful part. They're not all the same. And the reason why has everything to do with their neighbors, specifically the electrons hanging around them.
You see, a proton isn't just sitting there by itself inside an atom. It's surrounded by this fuzzy cloud of electrons. And for our detective story, you can think of these electrons as a team of tiny bodyguards protecting their proton.
And here's what these bodyguards do. That electron cloud creates its own little magnetic field that actually pushes back against the giant magnet we put the molecule in. It's like an invisible shield. So a proton that has a thick cloud of electron bodyguards is shielded, and it feels a weaker magnetic field. But if a proton is in a part of the molecule where electrons have been pulled away, it has fewer bodyguards. It's de-shielded, and it feels a much stronger kick from the external magnet.
And this is the whole key right here. The exact radio frequency needed to make a proton flip depends on the exact magnetic field it's feeling. So since the electron bodyguards change that field depending on the proton's location, different protons in different chemical environments will absorb different frequencies and send us different signals.
Okay, this is amazing news for our investigation, right? We're getting different signals from different parts of the molecule, but now we need a system. We need a standardized way to read and interpret this code so that every chemist in the world is on the same page.
And that system is called chemical shift. The best way to think about it is like a universal ruler or a map key for these signals. It assigns every possible signal a specific number on a scale. This means a chemist in Tokyo can look at a chemical shift value and know the exact same thing as a chemist in Toronto. It is the universal language for reading these proton signals.
And now for the final piece of the puzzle. How do we connect this chart of signals back to the molecule's actual 3D structure? How do we go from a list of numbers to a map? Well, the key is this really elegant idea called proton equivalence.
It's actually super logical when you think about it. If two protons are chemically equivalent, it just means they're living in the exact same electronic neighborhood. They have the same number of electron bodyguards arranged in the same way. So, of course, they're going to feel the same magnetic field and give us the exact same signal at the same chemical shift.
And if protons are in different environments, well, they're non-equivalent, and they give us different signals. Simple as that. And here it is. This is the big payoff. By simply counting the number of different signals we see on our spectrum, we instantly know the number of unique types of proton environments there are in that molecule. So if we see 3 distinct signals, bam, we know there are exactly 3 different kinds of jobs a proton can have in that molecule. We are officially starting to map the building.
So how can you tell if 2 protons are equivalent? Here's a neat little thought experiment you can do. Step 1. Pick any proton in a molecule. Step 2. In your mind, swap it out for some random test atom. Let's just call it Z. Step 3. See what new molecule you've just created. Now, step 4. Do the exact same thing for a different proton. If swapping out either of those 2 protons gives you the exact same final molecule, then those 2 original protons were chemically equivalent.
So, let's just quickly recap our detective story. We found our molecular informants, the protons, which act like tiny little magnets. We learned that their electron bodyguards shield them from a magnetic field, which changes the signal they send out depending on where they live. We then measure these different signals using that universal ruler called chemical shift. And finally, by just counting the number of unique signals, we figure out the number of unique proton environments, which gives us the first crucial blueprint of a molecule structure. We've cracked the code for protons, and it's given us this incredible insight. But protons, they're just one part of the story. This leaves us with a really fascinating question to think about. If this is the kind of detailed story we can get from the hydrogen atoms, what secrets are all the other atoms, the carbons, the oxygens, the nitrogens, hiding? And how do we get them to talk?